You can also perform a ring opening reaction of an oxirane or epoxide using an acid catalyst. In this case, I'm using sulfuric acid, and it will allow us to use water or an alcohol to open the ring in this process. The unique thing about this reaction is that if you have a tertiary location or tertiary carbon in the oxirane, it will want to open and attack that location, which goes against our SN2 type rules. So let's take a look at the mechanism, and then afterwards I'm going to talk about why the nucleophile will attack the more substituted location in this situation. So to begin with, down here, the sulfuric acid will be deprotonated by the oxygen in the oxirane. And now we have a positive charge on that oxygen, which makes that wanting to be even a better leaving group, which allows now a poor nucleophile to open up our ring. Okay, now we will introduce the methanol, and methanol will come in and will attack this tertiary location, and it will open the ring. Now when it performs this attack, it's going to invert that carbon. And so what you're going to see is these groups, which are pointing down, will flex and point upward. So what happened? We've kicked over the alcohol onto the left carbon. Okay, and we've flexed these groups and inverted them. Okay, now they're pointing up. And then we have our alcohol now attached. The last step is that we need to deprotonate this. So another equivalent of our acid, or the acid we just deprotonated actually, the HSO4 minus will come back in, deprotonate this hydrogen, and reform the acid. The reason I'm using the acid to do this again is because I mentioned this is a catalyzed reaction, so a catalyst will speed up a reaction and also needs to be regenerated in the process of the reaction so it does not get consumed. So here we go, we're going to now have our H2SO4 remade, and we have our product. Okay, so now let's take a look at why it will attack a tertiary location. Okay, so in this example here, I'm using the same example I just went through with the mechanism. You can see that the O that takes on that positive charge after it's protonated is trying to already leave without being attacked. And so it's starting to leave some partial positive on the carbon. Okay, so I've underlined the partial positive so you see where I'm talking about. So you have to ask yourself, which carbon can support the partial positive, the partial carbocation, better? Okay, so this is a tertiary location, and this is a primary location. And from our studies of talking about carbocations in our first semester and in review, you would tell me that the tertiary carbocation should be stable, or in this case, the partial carbocation that is tertiary should be more stable, which means that the oxygen's trying to leave and put the positive charge here. This is why the water or alcohol will attack a tertiary location in an acid catalyzed reaction. This only occurs with tertiary locations, and if you have a primary or secondary location, you will follow SN2 rules that are standard, and you will attack the less substituted location. So remember, this only occurs when you have a tertiary location.